Hi everyone, welcome to this video and welcome to my channel. So in this video, we are going to have a blast from the past, right? So we are going to discuss and then recreate a software or an application from past that I believe the majority of 90s kids have used, played with, had fun with, and pretty much most of us have loved it, right? So as it's already visible on the screen, it's none other than our good old logo where we had our good old friend the turtle, which would move around on the screen, go up, go down. You could basically control the turtle, do anything and everything with it, create patterns, designs, and things like that, right? So that's what we are going to recreate. I'm not sure about you guys, but I personally loved it. That was perhaps one of the very first introduction that I had to programming. I mean, if you think of it, it's kind of a interpreted language, right? You are giving it commands and you are basically making it do things on the screen, and that's kind of what we also do in programming, right? You give certain instructions, it follows a logic, and you get things done from your program. From a general purpose program, you can do many more things. On logo, you could only do designs, but it's kind of analogical to how programming works. And for me, it was one of the first introduction to programming, to computers and whatnot. So yeah, we are going to recreate logo from scratch, right, in C. So first we'll write a entire logo interpreter, not entire, but most of will in this video we'll cover the basic commands like the forward, back. We'll discuss about the commands. We are going to create the backend interpreter and the logo engine, which would be capable of taking in inputs, parsing it, and then evaluating the commands. And after that, we'll try to render the designs and all the movement on the screen using one of my other favorite C libraries, that is Raylib. So Raylib is a really nice tiny library with which you can create games. It's pretty much a wrapper on top of SDL2. It has simplified SDL2 to a greater extent, and it can get you started rapidly on designing your own games, building your own games, and things like that. So we'll be using Raylib to take our logo interpreter a step forward and actually render the things on screen. I hope this sounds exciting, and as always, without further delay, let's get started. Okay, so before we jump directly into creating our logo or writing the interpreter, let's try to understand what logo did, and especially for those who haven't used logo, since as I mentioned, it's really old and it's almost out of use now. Like no one really uses it. At least I haven't seen anyone use it anymore. But trust me, it's a very fun software, and we are going to enjoy building it. So what logo in general would look like is there would be a screen, pretty much a rectangular screen. So if I'm not wrong, earlier it would be just a DOS program which would draw directly on the screen, but later we started having emulators which would run on Windows and stuff. But earlier I believe it was simply a DOS program. And so usually what would happen is that the entire monitor or the entire screen would get divided into two sections. The first one would be the canvas, and the second section somewhere over here. And this is also pretty much the layout we are going to follow, right? So the above part is the drawing area, the screen, and the below part would mostly be for commands, like it's a commands panel or something like that. And in the center of the screen there would be a triangle, right? There would be a triangle, and here there will be a input panel, like for entering your commands. And what would actually happen is, like, there would be certain commands, and so there's just a triangle, but we would call it the turtle. That's like a logo lingo. And what would happen is you could enter commands. You could enter commands in this command panel, and you could control this turtle and make it move around in the screen. And while it would move, it would draw a line, right? And that's all. Using this turtle, you could then create your own designs, draw stuff, and things like that. So, for example, if I would want to move the turtle 40 units up, let's say, right? If I would want to move the turtle 40 units up, I could enter something like, I won't write here, but I'm just writing here the command examples. So if we would enter something like FD, which basically stands for forward, you could also write forward. If you would do FD40 and hit submit or press enter, what would happen is that basically the turtle would move 40 units up, right? It would move 40 units up. And then you could control the direction of the turtle as well. So if you would do something like RT90, it would basically turn the turtle right side by an angle 90. So the turtle would be facing this side. Now again you could do something like fd 40. The turtle would again move while drawing a line, it would move 40 units in the right direction, and so on. You could move it back. Let's say I wanted to go back by 20 units, so I could do bk 20. Back, bk stands for back, and the turtle would go back. It would come this side, it would come back for by 20 units, right? Some other commands would be lt, of course, to make the turtle face turn towards left by whatever angle you specify. So in this case again it would go back to the upward direction, or it would face the upward direction. And another very basic command would be home, which would simply reset the turtle's position and direction to the center of the screen, which is this one. So there is another basic command that is set xy, and then you could give coordinates, maybe 10 comma 20. So 10 comma 20 would move the turtle to that particular coordinate. So in this case, let's say 10. So let's say this much is 10 and this much is 20. So the turtle would come somewhere over here. Again, on digital screen or on computer screen, the 0 comma 0 is always the top left corner, right? So this side is plus v x-axis, and this side is plus v y-axis, which means if on anything on the screen, if there is an object on the screen, if you increase its x coordinate, it will go this side. If you increase its y coordinate, keeping x constant, it would go down, right? If you increase both, it would go diagonally, or however you are increasing it. And if you want to go to the opposite direction, if you want to go left, you reduce the x value. If you want to go up, you reduce the y value, right? So that's the convention that's followed on computer screens, and all graphic softwares usually follow that. So I don't remember what convention logo followed, but for our application, we would consider 0 comma 0 here. So whenever we are doing set xy, this whatever coordinates we are giving it, it would be with respect to this coordinate system where the origin is located on the top left corner, right? So that's basic logo. And some of the advanced commands, not advanced, but yeah, some of the intermediate commands I would say was pu, pen up. Pen up would basically ask the turtle to move without drawing any line, right? So if you, after doing pu, if you do, let's say if let's say the turtle is here, and if you do fd 40, it will simply move the turtle here by 40 units but won't draw anything, right? Again, there would be a pd command to put the pen down, which means again the turtle would start drawing. So one command which in comparison to these commands is a bit more advanced is the repeat command. So this command is really powerful, and like back when I was learning logo, this command was like, it gave me that element of awe, because I could do so many things with this thing. It has a bit of learning curve because it allows you to do nesting and stuff, but once you know this, you can do wonders with it, right, in logo. So for example, if you want to draw a square, so here's my turtle. If you see how a square is drawn, is basically let's say the square has a length of 20 units. So basically what you do is you go up by 20 units, you turn the turtle right. You could have turned it left as well, but let's consider that we are going to draw it in a clockwise fashion. Then again you go 20 units, again you turn right, again you go 20 units, again you turn right, again you move 20 units, and your square gets completed, right? So pretty much what you did is fd 20, then rt 90, fd 20, again rt 90, again fd 20, rt 90, fd 20. And just to make the turtle again face up what it was before, you could do another rt 90. So at the end of the entire procedure, what you will get is a square on the screen, and the turtle is again facing upwards. So if you see that you could manually punch in all these different commands one by one in the commands panel, and you could draw the square. But what if there was a way with which you could automate this, right? You could write once that, hey, I want to go, basically what you are doing is you are going 20 units up and moving and turning right by 90 degree. This you are repeating 4 times, right? So what if you could automate this? So exactly that's what repeat command does. So repeat command is logo's version of loop. What I could simply do is repeat 4 and then say fd 20, and RT90. So what it generally means is that it would repeat 4 times this entire section. So what it generally means is that logo will repeat this combination of FD20 RT90 4 times, and it will draw a square, right? That's what it will do. And with this, you could even draw a circle. Like circle would be pretty much like a basic circle would be FD360, and you could do FD1 RT1. So basically, it's for every 1 unit it's moving up, it's rotating right by 1 degree, right? And if you do this, what you will get, you will get a circle, right? And what makes this repeat command more interesting is that you could nest it, which means you could do something like repeat. I'm just giving a random example. You could do repeat something like 4, and inside again you could do repeat, let's say 10, and inside that you could do something like FD10 RT20. So what this means is that this entire repeat command, so basically this FD20 RT20 would be FD10 RT20 would be repeated 10 times, and this entire repeat combo would be repeated 4 times. So this thing would be, this FD10 RT20 would happen 10 times, and that multiplied by 4, so 40 times you would this total FD10 RT20 would get executed, right? And that's how you could nest repeat. So this repeat could have another repeat inside, and people would create crazy patterns using this technique, using repeat technique, right? Like crazy people would create stars and floral patterns and whatnot. However, we won't be doing repeat in this video. We would do it in the next video, hopefully. And because it would be really fun to implement the repeat command, so I didn't want to club it with this video to keep the video short. Anyways, I guess it would still become a bit long, but yeah. Okay, so that's the basic introduction to logo. And what we are going to do today is that we are actually going to build this layout. Like the upper section of the screen would be canvas, the lower section would be the commands panel. We would have this command input dialog, and I would additionally have a history box here, which would simply say what all commands have been executed, right? So I'll do that as well. So this will be history. Will be the interpreter right now we'll be building will interpret only a subset of the commands. We will do FD, we will do RT, we will do LT, BK, home, and setxy. We will go with these 6 basic commands for this video. And yeah, that's pretty much it. And the things that we want to do for now is that we won't do scaling. So when I'm moving the turtle by, let's say, 40 units, that 40 units will be static, and I won't be taking into consideration the length and breadth of the, or the height and width of the screen. Which what this means is that if tomorrow if you want to change the dimensions of the screen by some config to Raylib, this might get screwed a bit, because the units are remaining constant. The unit by which the turtle is moving up is remaining constant, right? Ideally, what we should do is we should scale given some imaginary target dimension for the logo screen and the actual dimension of the screen. Technically, we should do that, but for now we are not doing that. We will use static units to move the turtle up, down, and things like that, up, down, left, right. And yeah, that's pretty much it. And the other thing that I'm going to do is that I'm going to separate out the front end part. By the front end part, I mean is the rendering part, for which, as I mentioned, I'll be using Raylib. And for the GUI, I will be using RayGUI, which is again a Raylib library, add-on on top of Raylib. And the interpreter would be completely separated out, or you call it the logo interpreter or the logo backend. It will be completely separate in its own library, sitting in its own library. The reason I did it is, if you can in future, if you feel that you do not want to use Raylib, but if you want to use some other rendering library, you can do that as well. Although I'll still be using some structures or structs from the Raylib library, but again, changing those is very easy. Like if you have seen my previous video on creating a ray tracer, there I implemented an entire vector library for moving around, like plotting points on screen. You could simply use that as well. But yeah, keeping the interpreter and the rendering system separate, completely separate, and not coupling them together gives us this advantage of playing around with the different components. So yeah, that's pretty much it. And let's quickly set up a Raylib project, and let's set up our header files and everything, and let's get started. Okay, so the first thing I'm going to do is I'm going to download the Raylib template, which I've talked about multiple times in my previous video. it just allows me to get started with Raylib really quick. So this is the template, and all I need to do is do a git clone of the repo. Okay, and what I'm going to do is I'm going to rename it to logo. Okay, let's open it up. We've got a main.c. I'm going to remove all these. I don't need FiSAC for this implementation, and most of this will be just juggling around, and most of it will be moving to, some of it will be moving to the header file. But for now, let me just make sure that the window is coming up. Let me remove this, and okay, we'll call it logo. That extra L is just my quirk, nothing else. Let me get rid of all these things. We won't draw anything. All I need is just a blank screen for my smoke test. Let's close this. Okay, I guess that's fine. Clear background black, so we'll get a black background, or basically a window colored black. Let's just once build it. Yep, run it, and if you see, it creates a black window, 60 fps. Okay, so now that we have set up the Raylib template and Raylib is working nice and fine, let's get started with the actual implementation of the logo interpreter. What I'm going to do is I'm going to create, first thing I'm going to do is I'm going to create two files. Let's forget main.c for some time now. We'll be focusing completely on the logo library, which will contain the logo interpreter code. And okay, so for that, first thing I'll create is a logo.c file. This will contain the actual interpreter implementation, and we will also have a header file so that the other modules can access the logo.c functions. That's a logo.h. So let's start with some very basic includes and some very basic constants which we'll be using throughout this project, and then we will shift to once again discussing how we will be representing the turtle, how we'll be representing the lines the turtle is drawing, and how we'll be rendering it, right? So we need to make those concepts very clear, because before we can start with designing our logo, because the basic thing, if you imagine what logo does, is it keeps track of certain vectors and it draws them on screen, right? That's what it's doing continuously. As in when you are creating commands like fd20, fd40, the commands which actually draw something on screen. So logo is keeping track of all these point to point lines or point to point vectors, and it keeps track of them, and it's continuously drawing or rendering them on screen at a given fps, right? So we need a way to manage those vectors and keep them in memory somewhere, so that every time Raylib can access those bunch of vectors and it can draw them on screen, right? So let's see how we can do that. So first, let's do the guardrails, the header guardrails. If and dev logo header h hash define, so that it doesn't get, or the header file is defined in this header file, or the includes defined in this header file doesn't get included multiple times via different includes, right? We need to put this. This is a pretty standard thing in C, as we all know by now. And we will do a hashtag endif. So the libraries we want to define are malloc. We are going to do lots of string manipulation for our interpreter. Standard library. ERRNO, very important for error handling. Raylib.h. We will actually remove Raylib.h from main.c, but later. Then we will include remath.h for doing some, so for using some math functions, and then we come to defining our constants. The first thing is what's the direction it's facing when the program when logo is starting. So it's facing up, right? So and in Raylib and in most of the other game engines or graphic softwares, direction is always calculated from the positive x-axis, right? So towards right, it would mean you are adding degrees, and towards, if you are moving anti-clockwise, it's like you are subtracting degrees. So that's the convention that's followed in Raylib. So in a moment I will try to explain it in a better way by drawing it out on screen. But for now, let's just consider that the starting direction, to make the turtle face upwards, we need to give it a value of 90 degrees or 90 f in float. So I'll consider the screen width as 1200, basically 1200 pixels, and screen height as 900. So this is the entire screen width and screen height, right? The entire logo application's window size. Now we are going to define the canvas width and height. So I want the canvas height to be 75% of the total screen height, right? So 25% I will allocate for the command panel, but 75% is the canvas height, which would be same as the entire screen, just as we saw in the layout. So we'll call it canvas width is same as screen width, and canvas height is 0.75 into screen height, right? That's it. Okay, so these are our very basic constants, and before we move further, let's just see how we are going to, let's just try to understand how we are going to represent the turtle, its current position, its direction, its the lines it's drawing, the vectors it's drawing, and everything, right? So let's do that. Let's go back to our drawing board once. So the first thing that I was saying that we need to understand is, like, if this is our x-axis, right, and our turtle is facing upwards, like let's say our turtle is like this, it's facing upwards, so in reality it's making a minus 90 degree with the positive direction of x-axis, right? So this direction is always 0 degrees, and if you want to turn any object in Raylib towards the left side, you need to subtract angles from it, and if you want to turn it right side, that is clockwise, you need to add angles to it. That's like the basic convention, right, that we need to understand and follow in order to move things and draw things in Raylib. Okay, so keeping this in mind, the other thing we need to understand before we can start drawing on, or we can start moving the turtle around, is that, so if an object, let's say if an object like the turtle is moving upwards, all you need to do is change its y coordinate, keeping its x coordinate same. By changing y coordinate, I mean is subtract from its y coordinate to move it up. To move it down, what you do is you add to its y coordinate, right? Because origin is here, remember, origin is here. So when you add it, it goes down. When you subtract, it goes up, right? So that's how digital or computer screens work, or computer graphic libraries work. And if you want to move it right, you just add to its x-axis, keeping y constant, and if you want to move left, you just subtract from its x-axis coordinate, right? Now what if you want to move, let's say, diagonally towards this direction? So let's say that I'm just drawing it below. If you want to move the turtle at an angle of, let's say, I'm just not considering the angle direction for now, but let's say you want to move the turtle towards this direction, making an angle of, let's say, 40 degrees, right? Making an angle of 40 degrees towards the x-axis, or basically you want the turtle has been turned towards left by an angle of 40 degrees, and now you want to move the turtle to along that direction. So if you see in this case, it's both its coordinates, both its x and y coordinates are changing, right? Both its x and y coordinates are changing. X is increasing, y is decreasing because it's moving up at the same time. So what I'm trying to say is that the object is not moving across a single specific axis, but it's moving across both axes, right? Its x is changing, it's moving right, at the same time it's moving up as well. So how can we move an object towards a given direction, right? We cannot just increase its x and y randomly. We have to take into consideration this 40 degree, because it's going at a 40 degree direction, or at a negative 40 degree angle to positive x-axis. Like, we need to keep that direction in mind, which makes this entire line, let's say it goes how much, let's say it goes 100 units. So this 100 units becomes a vector, because this 100 units, it's not just a it's not just a scalar quantity, it's not just a physical 100 units in number, but it also has a direction, so it becomes a vector. And the easiest way to achieve this movement is breaking the movement down to its components, right? So if it's moving at 40 degree towards this direction, what we can do is, let me just extend this arrow a bit. So this is 40 degree, and let's say the turtle is here and it went till here, and this is 100 units. So what I can do is, and as I said, this is 40, and if it moved this much, which is 100, let's say from here to here it's 100, so we can take an x component, which is this one. This is the x component, and we can take a y component, which is this one. So if this direction become this unit, which is 100, becomes r, the number of unit, you can call it del r as well, but I'm just calling it r. So the amount it moved towards x-axis becomes r cos 40 degree, basically the cosine of the angle, and the amount it moved towards the y direction becomes r sine 40 degree. So if I want to move the turtle 100 units, right? If I want to move it 100 units at along a direction 40 degree, basically what it means is that I have done a RT 60 degree, right? So it was facing upwards. I want to move it along this direction, this is 40 degree. So basically what I have done is I have done RT 60, because this total is 90 degree. So 90 minus 40, I've basically done a RT 50. So that's why now the turtle is going towards this direction. Like, the turtle is going at an angle of 90 degree with respect to the y axis, but with respect to x axis it's going at an angle of 40 degree, which is this example. Let me repeat this again. So this turtle going at a direction at an angle of 40 degree with respect to x axis, actually what it means is that if the turtle was facing upwards, someone has done RT 50 degree. RT 50 degree has made the turtle point towards this direction, because RT 50 would make the turtle an angle of 50 degree with the upward facing y axis, which is nothing but also 40 degree with respect to x axis, right? Because the total is 90 degree and 90 minus 50 is 40, which is exactly this example. Okay, so let's say now we want to move any object, or in this case this turtle, for a given amount of units, let's say 100 unit, along an angle 40 degree with respect to x axis. All we need to do is we need to increase the x coordinate by x plus equal to 100 cos 40, and y minus equal to, because it's moving up, 100 sine 40. And that's how we sort our movement of the turtle along a given direction for specific number of units, right? That's how we basically move any object in a game world or a virtual world along a given direction, that is by breaking it into its components. Had there been a third axis, then by breaking it down into its components, when we are plotting it on a two-dimensional screen, right, or a two-dimensional canvas. So that's our direction and movement sorted. Now next thing, let's say I do a series of commands, like, so let's say the turtle is right now at 10 comma 10, right? So the turtle is right now at 10 comma 10, and what I do is I do a FD. No, actually, to keep things simpler, let's say the turtle is right now at a location called 100 comma 100, just to get some good numbers. That's it. Now I say I want to move it up by 20. So it goes somewhere over here, and now I'm not drawing the turtle, I'm just using points. So this is the first movement. I'm just denoting movements by numbers. What's the new coordinate? The new coordinates would become, x would remain the same, y would become 80, because I need to subtract 20. Now let's say I do a RT 90. Again, I'm following the square example. Now it will move towards it, it's facing towards the right side. So now the direction of the triangle becomes something like 0, because it was initially minus 90 and I wanted to go towards right side. I wanted to turn towards right side. So minus 90 plus 90, it becomes 0. So that's the current direction of the turtle, 0 degrees with respect to positive x-axis. Now if I do another FD20, now what happens is it comes somewhere over here. Let's say this is, let's say, the second movement or the second line the turtle draws, and this coordinate becomes 120, but the y remains same, so it becomes 80. And again, if I follow the same thing again, RT90 FD20, it goes down, and this becomes basically the x remains same, 120, but the y increases because we are moving down. And again, if we do another FD and RT90 and FD, so it comes back to its original position, which is 100, 100, and you can do the math. Basically you are going back now, so x reduces by 20, 100, and since it moved along the x-axis, the y remained same, and so y remained 100, right? And let's say this is the this is the third movement, and this is the fourth line. If you see that what logo needs to keep track of in this case are two things, right? It needs to keep track of the current direction of the turtle, right, which is cur dir. It needs to keep track of that, and it needs to keep track of a bunch of vectors, right? A bunch of line segments, I can say, or basically a bunch of paths, right? Or path segment, whatever you call it. I'll call it simply path. So if it needs to keep track of number of paths. It's like 1, 2, 3, 4, 5, 6, and whatever number of paths you draw. So let's say, again, I'm using P1. P is usually used for points, but let's just consider P is path. So P1, P2, P3, P4. So all that Raylib needs to do in its every render cycle is nothing but render these paths or draw these lines on the screen. That's it. It has to do nothing. And at the end of drawing all the line segments, so there is a third thing that the logo interpreter or the logo backend needs to track is the current position of the turtle. Very important, right? So cur dir and cur pos, right? Cur pos is nothing but x comma y coordinate, right? That's it. It's a vector position or a position vector, whatever you call it. So it just needs to track two numbers like x coordinate and y coordinate, the direction, and a list of such paths, P1, P2, P3, P4, P5, whatever, so that Raylib can first render all these line segments, and at the end it can just render our turtle at a given position at a given direction, right? That's it. So now if we observe that these paths can be further broken down, right? So what is a path? If I consider this path P1, what is this? It's nothing but a tuple of two coordinates, right? It's a tuple of 100, 100 and 100, 80, right? So basically all these paths that logo has to track for us is nothing but each path is nothing but a collection of two coordinates, a source coordinate and a destination coordinate, right? So what we are actually doing is whenever we evaluate a command, or whenever a user inputs a command which actually moves the turtle from one place to another, which is actually supposed to move the turtle from one place to another, like mostly in this case FD and BK, we need to create a path which is, or somehow in C we need to represent such a path which is nothing but a vector consisting of a source point and a destination point, and we need to store it in a list. So in C we can represent such a point or a coordinate using nothing but a struct. Raylib in this case already provides such a struct out of the box. It's called a vector. And to represent a path, again we can use a struct which internally consists of two such structs, a source position struct and a destination position struct. And the next question is how then we can maintain a bunch of such paths. It's very easy. We can implement our own linked list, which is pretty easy to implement, and that's how we are going to store this bunch of, as and when the movement commands are evaluated by our logo interpreter, it will create a path and it will put it in a list of paths, which is basically a linked list of paths. And then all that Raylib engine has to do is simply in its drawing loop, it needs to continuously render all these series of paths and finally render the turtle at a given position with a given direction. That's it. So this is how our basic logo interpreter will work. And so yeah, that's pretty much it, how the backend mechanics will work. Now we are at a good position to jump into code. So let's do that. Okay, so let's get started with creating the structs that we'll be needing to track all these things that we discussed so far. So the first struct or type def that I'll be creating is the one for storing a path, which like path here means the basically the segments that the turtle will move, just which we just discussed. And as we said, it will be nothing but a combination of two coordinates, a source and a destination. And for coordinates, we'll be using the vector2 struct, which is provided out of the box by Raylib. And we will call this struct path t, basically this type def path t. Next, we want a linked list which consists of many such paths, right? So next, I'm going to create a struct for the path node, which will be used for the linked list. So each path node will actually contain a node and the next pointer, just like how we do in linked list. Path struct path node star next type def struct path node, and I want to call it node t, path node t. Next, what I want to do is that I want to have a type or a struct for representing every command that the user inputs, right? It's just for the ease of processing. So I'll have this struct and type def called a command underscore t, a command type. And if you remember, every command in Logo is of the type except maybe the repeat command, which can be nested. Most of the commands in Logo are of the type operator and then operand. So the operator can be fd, bcan, things like that, and an operator can be or cannot be present, may or may not be present. Like the operand or the value can be numeric, or it can be nothing in case of home, or it can be multiple values in case of set xy and things like that, right? So I'll keep it simple. I'll have one string of length 20 for operator and another for the val, or basically the operand. I'll keep it a bit long. I'll take 100. We might have to increase it depending on how we do the repeat command later. We might have to change it, but for now I'll just keep it 100 and I'll call it t. So these are our basic structs. Now in logo.c, the first thing of course that I'll do is include logo.h, and we'll create the head node of our linked list. That's pretty much the first thing that we need. So path node head, we'll call it path node head. Then some of the initial conditions, or the initial configurations, we can call it, that we want is that the initial direction of the turtle, which will be like float direction, and that should be direction start. Then we need the origin where the turtle will be located when logo starts, and that should be canvas width divided by 2.0. So I want the turtle to be present at the center of the canvas, right? Not the center of the screen, that includes the panel as well, but the center of the canvas. Canvas height by 2.0. And I need to track the current position as well. So for that we'll have current pos, and for now it will be same as our origin, because yeah, when logo is starting, the current position is pretty much the origin, right? Okay. Next, we want to have something called the command log, and that would be nothing but a pretty big string. That's it. So this log is actually which will implement the history panel, where we will have a history of all the commands that has been entered by the user. Now let's create some helper functions. I want to create a function for creating a path. Like all it will do is it will return me a path type struct, which is nothing but a struct consisting of two vector points, that is vector2 Raylib structs, source and destination. So but I just want to have a tiny function to help me create that. create path vector2 source, and so it will take two vectors, of course, or two vector structs. I'll typecast it to path t. Source will be source and destination is destination. This is just a simple interface, like a interface function for getting the current position. We will expose this function in the header file so that Raylib can access this function, right? Rather than defining this variable as an extern, which is not a very good thing to do, we will just encapsulate it in this function and call this function from external modules like our main.c. Same we will do for get cur dir. It will just return the direction. Oh, it should be float, my bad. Then we can have another helper function to return the path head. And now we want another helper function to create a path node, right? So a path node is nothing but a path and the next pointer. Path node t, create path node path underscore path. So it will take a path because that's a path we want to put in the node. And now we'll create the node using our good old friend malloc. Okay, why does it say it's not defined? That was a typo. So now we need to set the properties of this node. So pnode dot path equal to path and pnode dot next equal to null, and we return pnode. Next, I want to have a function that initializes the various configurations when logo comes up. As of now, it will only initialize the history. That's it. In future, we might have more stuff here. Basically, by initializing the history, I mean it will initialize the command log variable. Size of char into 1024 into 1024. So that gives me 1 MB, right? And I will mem set it to 4. Oh, that should be a there should be a star. Okay. Again, I need a function to get the log. So command log. And how do I log a command string? Again, I need a function to actually add a command, like whatever the user has provided us to the history. So for that, I'll create a function called log command. Wait, log command. I'll just concat existing command log with a new line, and again I will concat command log with command str, so that the new input just gets appended to the log, right? Okay, now another fun part. or another fun function, our function to add a path to our list of paths. So if path node, and it's a pure linked list addition of a node, right? Like how we add a node to a linked list. So if head is null, we can't do anything. We have to initialize the new node as a head node. Create path node and we send the new path. That's it, and we return. Otherwise, we do linked list traversal and add the new node at the end of the existing list. So path node t p, yeah, tp node. Why tp node? Temporary node, right? So what I do is I basically make it point to the actual existing head, because we don't want to lose head, right? Classic linked list traversal. I always love linked list, one of the best data structures out there. Easy to implement, simple, does its job. tp node equal to tp node dot next. So I'm making the current one go to the point to the next one, normal traversal, unless and until next is null, which means we have reached the last node. So now we have reached the last node, and what we'll do is we'll make the next pointer of the last node point to create path node path. And now that pretty much completes our path addition function. Finally, we have got, now this is not something we'll be needing, but it's just for debugging purpose. What we want to do is have a function that pretty much shows all the paths that we have in our list, right? It helps for debugging purposes. So we'll just do show all paths. Again we'll have a temp node t underscore p node equal to path node head while p node not equal to null, we do printf. So source, basically it's a path, right? Source to destination. We'll just put it in a nice way so that it's easy to read in the terminal when it prints it out. Let's put it in bracket %lf and a new line, and now let's just do pnode dot path dot source dot x to pnode dot path dot source, of course, dot x, and then same thing but for destination nodes, destination coordinates. So t dot pnode dot path dot destination dot x comma pnode dot path dot destination dot y, and that's it. Yeah, nothing much is happening here. We traverse the linked list and we print out stuff, and then tp node equal to tp node dot next. We just move to the next node, right? And these are all our, all the functions that we need to deal with our paths, right? With this setup, now our logo interpreter or our logo engine would be able to track all the paths that has been drawn so far, and so that Raylib can render them on screen, right? Next, let's start with the functions that will actually evaluate commands, right? So what we'll do is that for every command we will have a evaluation function. So for FD we will have a eval FD, for BK we'll have a eval BK, so that we know which function to call for which command, and then we'll write a central parser that will parse the command, and on the basis of what input, what command that has been provided, we will call a particular evaluator to evaluate that command, right? We will have a number of functions. We will have one function per command, and we will have a central parser that will parse the command and use the corresponding command evaluator to actually evaluate the command and do whatever it wants to, what it needs to do, right? So let's start with the with the evaluator functions, right? So the first one, my favorite, eval fd. Actually, before we go there, let's update our logo.h with. Actually, no. Let's update logo.h with all the functions, function definitions. Sorry, the function declarations after we have done with the actual implementation of the engine. Okay, so yeah, coming back to eval fd. Char. So what will eval fd take? It will take a operand, right? It will take a value which is pretty much the number of units by which it needs to go up or basically move forward, right? I mean, I keep saying go up because in my mind the initial position of the turtle is center facing upward, but fd means just move forward, right? It can be towards along any direction, but we just need to go forward, and backward means backward along that direction. So first I need to parse val str into a float, right? So I'll just use usual C float parsing. So this is just a smoke test wherein if the length of val str is 0, we just return -1. -1, I'm considering -1 as a global indicator of failure to evaluate a command. As of now, we'll just return -1. In future, what I plan to do is, along with this, I'll take a pointer to a string where I will actually put in the error that happened, why the command failed, and we can show it in our history and in the panel, in the command panel, like why the command execution failed and what was the reason. For now, I'll just return -1. I'll use str to f and I'll send value as val str and nptr. So I'll just initialize ern 0 to 0. Sorry, I'll just initialize errno to 0 at the very beginning. If errno not equal to 0, that is, there was some issue while parsing the float value from string, or endptr is not equal to null string, that is, nothing is remaining to be parsed. Nptr, if nptr has something, it means there is a string which C couldn't parse into float, which means there was an invalid value in the string which can't be parsed into float. Anyway, so if the parsing fails, we just return -1. Now another fun part, we need to calculate the new position of the turtle, right? Because we are moving forward by a certain value. So new pos equal to, and here our trigonometry knowledge comes into picture, which we just discussed, where we break the motion into components. We break the delta movement into components, a component along x-axis and component along y-axis, so that accordingly we can update the x and y coordinates. So curpos dot x plus, so the new position would be the current position plus the amount by which we are moving forward. So cos f direction, and the cos f comes from Raylib remath direction into, and these library functions always work with radian, not with degree, so we need to convert it into degree first. Into val. What's val? Val is the amount of the delta by which we are supposed to move forward. So remember, it was like if we want to move forward by 100 and the direction is 40, so we need to take 100 cos 40, 100 sin 40, and hence value is basically 100 here. I mean, like according as per our example, value would actually be 100 in the example that we used. And cur, then we have to update dot y as well, plus sin f direction into tag to rad into val, and that's it. That's our new position where it will go, where the turtle will go. Now what if this new position is beyond our visible canvas? What if it goes into the panel area? What if the turtle goes out of the screen, right? In that case, we don't want to actually add this path, or we don't want to evaluate this path, and we just want to return -1. So for that, we actually need a boundary checking function. Let's quickly define that. Check in canvas vector 2 pos if pos dot x less than 0, that is it's outside beyond the left edge of the screen, or pos x dot x greater than canvas width, which means it's beyond the right edge, or pos dot y is greater than is less than 0, which means the upper edge is breached, or pos dot y is greater than canvas height, which means it has breached the upper edge, which means it has breached the lower edge, my bad. Then we return false, else we return true. And really uses, I mean, if you go to false's definition here, yeah, it comes from std bool.h. I have not included it. Have I included it? No, I have not included it, but I believe it's coming from Raylib, which is fine. So this is our boundary check function, and now what we'll do is if check in canvas, if check in canvas new pos equal to false, we return -1. Now we create a new path, and y is, oh, I missed semicolon here. And now we create a new path, create path, cur pos and new pos, source and destination, and we simply add path to our linked list. And very important, we need to update cur pos with new pos, so that becomes the new position of the turtle. And if everything goes well, return 0. So that's our simple forward function. Next, very similar to the above, we need to create eval bk. We could have combined both of these into one function, but I just wanted to avoid if else. If strlen val str equal to 0, then return -1. Then our usual stuff, end ptr for float parsing, and we set err no equal to 0. Then we do a val strtof val str. Now if we just have to do the check if no not equal to 0, or star and ptr not equal to x is 0, return -1. Vector 2, again we calculate the new position, and this time we do just the reverse. Instead of addition, we do subtraction, because we are moving backward. Direction into tag to rad into val, comma, cur pos dot y minus sin f into direction of direction into dec to rad into val. Once again, we need to check if we haven't moved back enough to go out of the screen, whether we have moved backward enough to go out of the canvas. If so, return none, return -1. Next part is again same path equal to create path, cur pos, new pos, add path, add no cur, we need to update cur position with new position, and return 0. That's our forward and backward function command evaluator functions. Now we need to evaluate rt command, val str. Same thing again, I'll just copy paste from here, and I'm going to I'll just copy paste from here. If val str is 0, then return -1. Do the parsing, and then remember we are moving right, or we are turning right, so we do a plus equal to val, return 0. As simple as that. Now let's do eval lt. again. Well, actually, you know what, I can simply copy this and I can paste it, and the only difference is instead of plus it will be minus. Okay, easy. Yep, the name needs to be changed, lt. Now we need to eval our home command. It accepts no argument, as we just saw. It just resets the direction and position. So we will reset the current position to origin. Direction will get reset to direction start, and I return 0. The next one might seem a little bit lengthy, but it's mostly parsing. The real part is really tiny, so it's eval set xy, which moves the turtle to a certain position on the canvas. It accepts a val underscore xy. What do we do here? We first once again check that if val xy equal to 0, we simply return -1. Then we create the same again, float parsing equal to 0 cons. Now we need to tokenize this to, so by tokenize I mean what are we expecting in val xy? We are expecting two numbers, we are expecting two floats. Again, these are all integers, but I have just taken them as float just in case. You can also play around with integers, it's fine, but I'm just going with float. So what is val xy? Is just two floats divided by a space. So we can simply use a tokenizer here. So car const car, what will the delimiters? We are going to use the strt okay, or str string tokenizer function in C. It needs the delimiters as a string. We only have one delimiter in this case, which is a space, and then let's extract val x, which is the x coordinate. Strt okay, val xy delimiters. Okay, if val x equal to null, we return -1. Once we have val x, we need to do our good old float parsing. TOF val x comma and ptr if errno not equal to 0, or in ptr not equal to, actually I have done a few mistakes here. These shouldn't be string, this shouldn't be string, this should be a character, because we can compare the characters in C, not string, remember? Like, so the first one was correct, after that I did the mistake. Anyways, what we do, we simply return -1. Next we do the same thing for val y, and equal to strt k if val y equal to null. Oops, we return. That's just the normal how string tokenizer works. The only the first time it needs the actual string. After that you can simply go on with null. It has the string initialized internally. Once again, float pos y equal to strt with and ptr if errno not equal to 0, ptr not equal to okay. So we are done with all the float parsing, the tokenizing and everything, and all now we are left to do is update the current position of the turtle, and curve pos y equal to pos y return 0. That's it. That's our eval set xy. And then comes our parser, basically the command, basically the function that will parse our string command into a command type. And so that we can evaluate it. So we'll call it parse command char star command str command t command cool. We just memset command with 0. Okay, so far so good. While star, now what we are actually doing is we are going to go over the command string byte by byte or character by character. Initially it might happen that the user gives some empty spaces or white spaces at the beginning of the command, so we just have to get rid of those. Right, we are just moving it forward. Then let's create some string variables for the operator. We already have some predefined sizes, right? And in op length, so like at what index of the operator we are right now, that will help us in parsing. So while star command str not equal to empty, that is we are actually parsing some legit characters like non-empty characters, and command str not equal to the null string or the null character, which means we haven't reached the end of the input string. What we can simply do is op plus op underscore length. Remember, op length initially is 0 equal to command str. It's just simple character copy from one string to another. That's it. It just makes sure that the value at op plus op length, so op is initially the starting of the character op variable, plus op length, which is 0, so it actually means it's the starting of the string. So the character at that position will be the first character present in command str, right? And then we just increment our counters or our loop variables. So we increase length by 1 so that next time it copies to the next position in op, and we also increase command string by 1 so that we can copy the next character. And then we just move, after the copy is done, we just move at the last character of op, or the operator string should be nothing but, it should have a string ending null character, right, which makes it a proper string. And then what we do is that we simply do a str cpy to copy this operator that we extracted to command's op property, right? So now we have the operator. Okay, and then what's our format? Our format is, forget about repeat. Without repeat, our format is like operator space, there may or may not be another operand, and operand is nothing but another chunk of string or a chunk of continuous characters, right, to the end of the string. Now that might again contain white spaces, because for example if it's set xy, so set xy's format is set xy space x coordinate space y coordinate, but that parsing will be taken care of by the set xy evaluator function, right? We just want to get the entire operand present after operator, which is basically the part of the input string minus the operator, pretty much the entire input string apart from the operator. That's our value for the operand. So let's skip again any white space between the operator and the operand. So while command str so now command str is nothing but the operand till the end of the string, right? So if our operator is one of the operator that requires an operand, then we will populate the value property of our command struct with the operand, right? So yeah, it will be clear in a moment. Command.op. So if the operator is fd, let's just make it look a bit nice, or let's copy it. how many times? 5 times, right? I should have copied with this as well. Yeah. How many times? 5 times. So now bk or rt or lt set xy. Then what do we do? We simply do strcpy once again, and return command. So now our command is fully formed, right? We are all good. Our command is fully formed and it has the operator and the operand if needed and if present, and then we return the command, right? Now we need to create a central evaluator function which will see what kind of operator is present in the command, and it will call the correct evaluator function to evaluate that command, right? So for that we will do nothing but evaluate command. So this is the one that ties up the parser and the evaluator functions, and this will be the actual function that will be called by Raylib when it gets an input from the user. So first I will log whatever I'm getting. I will log it first, right? Then let's parse the command. Now if strlen command dot op equal to 0, then that's invalid command. We return -1. Now if the operator is fd, then we just do eval fd. If it's fd, then we call eval fd with the value. And next what I'm going to do is I'm simply going to copy it a few times. Okay, so fd, then pk, it will be eval pk rt eval rt lt eval lt home eval home, and finally set xy. That's all our 6 commands for now. Eval set xy. And if it's none of our expected commands, then simply return -1. Okay, so that's pretty much our entire logo interpreter. Let's just quickly expose these functions in our, or put these function declarations in our header file. Vector to get cur pause. We have got float get cur dir. Let's see if I can, divide my screen. Okay, we have got void init logo. We have got char get command log. Void, we have log command. Again, some of the functions you might not want to put in logo.h. You might just want to put them at the beginning of this file itself, so that ordering is not required. I'm just putting it in logo.h. Usually you put something in the header file when you want to expose it to some other module, but in this case I'm not just following that convention. I'm just putting everything here. Create, for example, create path will never be needed by Raylib never doesn't even need to know about create. Like our main.c doesn't even have to know about create path. Like the renderer doesn't need it. Then we need the, there was something called Then we have path. After create path, we have got get path head. Path underscore t. No, path node t star get path head. Star create path. We want the create path node as well. Create path node, and I believe it will take a path t variable. Yes, create path node. Then we have got what else do we have? Oh, we have got a lot actually. Add path underscore t path. We have parse command, and we have got, let's do the parse and evaluate void. Sorry, we have got command t parse command, and it takes a string. We've got evaluate command star. We have got the next one's actually it's easy to just write char star int eval pk char star int eval rt char star int eval lt char star int eval home int eval setxy. Oh, it needs a, and then finally void show all paths, our debug function. That's it. So that's all our functions, and that's our complete logo interpreter for the 6 commands that we chose. And next we need to write a renderer so that it basically use Raylib to render this paths on screen and create our command panel as well. So let's do that. So now we are back in our main.c, and let's just get rid of these comments. Basically, let's just get rid of everything because we'll be redoing everything. Yeah. Okay. First thing, we don't need raylib.h here anymore. Why? Because our logo.h will take care of all the header inputs or header includes. So we just have to do logo.h here. Now, first thing, let's get rid of these as well. Okay. So now the first thing we'll do is initialize our window, and here it will be screen width, screen height, and we will say logo. Next, we'll just call our init logo function, remember, which will initialize, for now it will just initialize our command log or our command history. Next, we'll just get the command log as well so that we can display it. Right, and actually we need to set up now quite a few variables here, which will basically configure the positions of our different command panel widgets, like the input box, the history panel with the scroll bar and everything. But before that, let's do the first things first, which is let's write the code which will print or show, which will render the path of the path traced by the turtle. So that will happen completely inside the drawing section of Raylib. So first we need to do begin drawing, and then I'll do a clear background. Just before we draw the next frame, I just want to get rid of everything and make it white. It's just a standard procedure. The next thing that I'll draw is the GUI group box. It's like a panel which will determine the command panel area. We call it GUI group box, and yeah, rectangle. So it basically takes a struct of type rectangle, which means the first will be the x and y coordinate from where the panel will start from. So the x coordinate will be 0, the y coordinate will be just where the canvas ends, which is canvas height. Then what would be the width? The width would pretty much be the screen width. Then height would be, so the height would be the remaining space of the screen, right, where that is the entire screen height minus the canvas height, right? So this minus canvas height. And it also allows the GUI group box also allows you to put a tiny text on the top right corner of the panel border. In this case we will simply write command control. That's it. Next, what we are going to do is we are going to trace the path or render the path, whatever you call it. So first we will get the head node of our path list. P node get path head. So now we have got the head, and the head is pointed to by a temporary node, which is TP node, and while TP node is not null, we will draw a line. So for each path in the paths list, we will draw a line, and that's what it is basically, right? We are just going to, logo is just maintaining a bunch of paths for us, and the renderer is just going to render those paths in form of line segments, right? So draw line extended, and draw line X is just a variation of normal draw line, which also allows you to provide a thickness for the path, right? And also it takes the source and destination in form of vector2 structs, which is exactly what we want, because in our path node, so basically our path struct consists of 2 vector structs, right? One for source and one for destination. So we'll do path dot source and TP node path dot destination, and I want the thickness to be 4 and the color to be black. And then I point the temporary node to the next node or next component in the list. Next, so after we have done rendering the path, we need to draw the triangle or the turtle. Draw poly, get curve pos, and let's use the maroon color. Actually, I can use red as well. Does it provide red? Let's see. Yeah, red. So draw poly, get curve pos, and so 3 and 10 is nothing but, you know, the length of the side. I want, sorry, the number of sides, which is 3 because it's a rectangle, and the length is 10. One thing with this is it will draw a equilateral triangle. So since it's an equilateral triangle, one problem that we'll have is that when we are using the RT and the LT commands and we are making a 90-degree rotations, sometimes it might happen that you won't understand that it's actually rotating because of the symmetry, right? But that's fine, right? Once we use the FD or the BK command, we'll know whether it has moved, whether it has rotated in the correct direction, and also we'll have the command log to see what is the last executed command. Okay, so that's the main rendering part done. Now we need to define certain variables for the various GUI components. Let's do those. First, a variable for our command input, very important. Then it's just a variable to define the mode of our input command box. Next, we need a label. I want a label for the command input form, which will just show what the input widget is meant to do. It's just so that you know that's the place where you have to enter the commands. So here's the config for that. Command box label x equal to 40. In command box label y equal to So I wanted to start a bit below the canvas. So canvas height. I could have also written this relative to the panel position as well, but yeah, it's fine. It's the same thing at the end of the day. So in the command box, label Y. Okay, so now we have the command box label width and height. That's pretty much static, right? It's just a label. Next, we want the command box width, and this is the actual command input box, right? The actual command input widget. Height can be just 40. And this is finally the box coordinates. Command box (24). So those are the configuration for the command box. Now we come to the log box or the command history box. So int log box width, I want it to be a bit wide so that people can read the history nicely. And height can be static. I'll be anyways using a scroller here. And finally int log box x, that is a x coordinate. So x coordinate would be width by 2. So I want it at the beginning of the right half of the panel, of the command panel. So that's why command width by canvas width by 2. And this is just all relative, like, so just where the canvas ends plus the log label height, because I want it below the log label. Okay, I believe I forgot to define it, but that's fine. So log label x equal to canvas width by 2. Same thing. If the log box is on the right half, the label also needs to be on the right half. Int log label y equal to canvas height plus 14. Int log label width equal to 140. Int log label height equal to 16. So now I can use it here. Log label log box y equal to canvas height plus log label height plus 24, and then finally log content. So this needs to be really big. So this will be hidden, and this is which will actually contain the history, and it will be controlled by the scroll, basically the scroller, right? So box width, it's just how Raylib defines scroll bar, right? Nothing much that I am doing here, just following the Raylib guide. Cool. Finally, the scroll bar or the scroll area also needs a panel view. Again, just following the Raylib code. Nothing much to customize here. Vector to panel scroll equal to 1.00, 0.0. My bad. Okay. Finally, we defined the boundaries for the log or the struct for the log box, basically the history box, and the log content box, which will actually actually hold the content and which will be scrollable. Rectangle equal to rectangle log box x log box y log box width, log box height. That's it. And rectangle content zero zero content box width, law content box height. Done. So this will be braces instead of parentheses. So now we just need to draw these GUI components. We have them configured. We have the configurations. So now we just need to use the configuration and draw them. So drawing GUI components using Raylib is pretty straightforward. You just have to follow the raylib.h header file code and just do whatever it wants, right? So not much of a customization here. So I'll just draw the GUI components one after the other, right? So this is the label for the command box. So that's what we want the label to show, that is enter command. GUI set style is used to set certain styles for text and overall for Raylib GUI. Even if you are setting any style here, remember that all the components that you draw after that will follow that style. And so it's better that after you are done with your drawing, you reset it to the version that was before or to some other version. The bottom line is, whenever you set a style, all the GUI components that would follow would respect that style. So this command input variable is where the command that is provided by the user will be stored. Raylib takes care of it. It will copy whatever you enter into this variable. You don't have to do it yourself. 64 is the buffer size, which is already 64, which is already pre-decided. And this variable tracks whether the box is in edit mode or not, right? You will just toggle it whenever someone puts the cursor in the command box. Okay, so now comes the GUI label for the history box or the log box, which will show the log of the commands. And it shall read history. Now we are going to create the scroll panel, and the scroll panel is very it's just once again, as I said, I'm just following the Raylib code, Ray GUI code, nothing else, and I'm just doing whatever it wants me to do. So Caesar mode actually defines the area that's scrollable. So that's a typo. It will be Caesar mode. Yeah. here we are actually drawing the text box that will be scrolling, the bigger one, which will actually contain the content, right? So that's why we are putting log here, which is the actual string containing the log, and then we have the buffer, which is 1 megabyte, and false. Why false? Because we do not want this to be editable. It will just show the history of the commands. And that's pretty much it. Okay, so there is one thing that I haven't done yet, and that's very important. So sending the command provided by the user for evaluation once user hits enter. So let's quickly do that. Without that, we'll just be entering commands, but nothing would happen. So let's do that. So just before we start to draw, in every frame, what we'll do is we'll check if the command box is in edit mode, which means cursor is present in the command box, or maybe user have been typing something, and when user presses the enter button or the enter key, if we do a smoke test whether it's a blank command, only if that's not equal to 0, we call our evaluate command function, which we created in our interpreter. And then we once again mem said command input to 0. And that's pretty much it. That's our logo renderer, along with the GUI panels and everything, and the interpreter which we have already written. And now let's try to compile this. And it compiled. Now, moment of truth, let's run it. And look at that, that's how it looks. So we have the bright red turtle, the canvas area, and the command panel area, right? Here where you can input command, the history panel, the history area or the history box, and everything. Now let's try to play with some commands. And it works. So FD40 moved the turtle up by 40 units or 40 pixels, and as you can see in the history, FD40 came here, like, right? Because that's what we just now entered. Let's try RT, and the turtle rotated by 90 degrees. So since the current position of the turtle is the center of the polygon, right? So that's why it's overlapping with the line, but that's fine. We can live with it for now. And now let's do again FD40. Let's do RT90 again. FD40, RT90, FD40, and again RT90. And we have a square, right? We have a square done using the logo that we just now built. Let's try something else. Let's try the BK command. Let's do a BK 100, and it worked. We moved down by 100 units. Let's do something else. Let's do a LT. Let's do a LT. How much? Let's say LT 35. And now let's see if we can draw a line along this 35-degree direction towards left. And it worked. Let's do a BK from here. We could do a BK as well. Let's see set XY. So I'm going to move it to 10 to 100. Yep. So the direction got preserved, and we just moved it to 10, 200. What if I move it to set XY 100, 200? Okay, it moved along the x-axis because it was already on 200 on the y-axis. So now let's draw something once again. FD 100. Yep. So it was facing that side. So that's why it went along that 35, because we had done a LT 35 previously. And now let's try to do a home command. and it came back to the starting position. So that's our logo interpreter and renderer from scratch, implementing 6 basic commands, and it's all working as expected, right? So yeah, that's pretty much it. I wanted to build this basic logo interpreter and renderer. Hopefully in the next video I'll be implementing more stuff on top of this, like the repeat command. If any one of you want to create the repeat command, just let me know in the comment section below, or in this entire code will be available on my GitHub as well. You can simply fork it or send a pull request to do whatever changes you want. Play around with it. I would request you all to play around with it if you want to have some fun with logo. There are also several logo interpreters present online, hosted online, which is like the full-blown logo suite with all the commands and everything. You can try out those as well. Pretty fun. Do let me know in the comment section as well how many of you used logo, what all you did with it, what all designs you made, if you remember, of course, because it's a pretty old, as I mentioned, it's a pretty old piece of software, right? And I really loved using logo, right? When the first time I got introduced to it, it was really cool because it allowed me to, like, as I mentioned, it allowed me to interact with the computer. It was like I'm doing something and I'm getting the feedback instantaneously, right? I'm writing commands and I am able to make the turtle move around, and that feeling was really great. Like, it was a cool experience when I did it for the first time. And also let me know, how did you boot logo for the first time? For me, I booted it from a floppy disk, right? Because it was a really tiny piece of software, right? You boot it and it opens up in DOS. After that, I guess there were emulators for Windows and stuff, but yeah, initially I believe it was on DOS. And yeah, it was really fun using logo. I really loved it. So let me know how you all booted logo, whether you all knew about logo before this. And yeah, that's pretty much it for this video, and let me know if you like this, and thanks for watching, and see you all soon.